All right, let's talk about a ghost that haunted the field of artificial intelligence for decades, the vanishing gradient problem. Now, understanding this one single barrier is absolutely key to understanding the explosion of deep learning we're all seeing today, because for a very long time, this problem nearly stopped the entire field dead in its tracks.
So let's start with the big question. We want to build these unbelievably powerful, deep neural networks. I'm talking hundreds, even thousands of layers deep. But how in the world do you actually teach something that complex? I mean, really think about it. How do you tell the very first layer if it made a good or a bad call, when the final answer is thousands of steps away?
Well, the way a network learns is through this process called backpropagation. The best way to think about it is like an echo. The network makes a guess, right? We check how wrong that guess was, and then we send a correction signal, this kind of echo, all the way back through every single layer, telling each one how to adjust. But what happens if that echo fades to a whisper before it even reaches the beginning?
And that, right there, is the vanishing gradient problem. The gradient is really just the fancy math term for that learning signal, that echo. As it travels backwards, it can shrink. And not just shrink a little, but shrink exponentially. So by the time it gets to those crucial first layers, the signal is so faint, so close to zero, that those layers are effectively deaf. They can't hear the corrections, so they just stop learning. Now, just to make things interesting, this problem also has a kind of evil twin, the exploding gradient. It's the exact same idea, but in reverse. Instead of the signal shrinking to nothing, it gets exponentially bigger and bigger until the network's updates go completely haywire. So you can see the challenge, right? You have to keep this learning signal in this perfect, just right Goldilocks zone.
And this isn't some new discovery, by the way. This problem was formally identified way back in 1991 in a thesis by a guy named Sepp Hochreiter. All through the 90s, researchers kept running headfirst into this wall, confirming just how badly it crippled their networks, especially the ones trying to learn from sequences of data. This was the big monster they knew they had to slay. Okay, so why does the echo fade? What's actually happening here? The reason, funny enough, is rooted in some pretty simple math. My favorite analogy is making a photocopy of a photocopy. You know what happens, right? Each time you make a copy, the image gets a little bit fainter, a little more washed out. If you do that 100 times, you're just left with a gray, blurry mess. The same exact thing happens to our learning signal. Here's the play-by-play. As that signal travels backwards from one layer to the next, it gets multiplied by the parameters of that layer. And that repeated multiplication, that's step 4 right there, that's the real culprit. This was especially a problem because a lot of the tools they used back then, like certain types of activation functions, had a nasty habit of producing values that were less than 1. Let's make this super concrete. Imagine our learning signal starts out with a pretty decent strength. Let's call it 0.9. Okay, strong signal. It passes back through just one layer,
And bam, it shrinks. It's already weaker. Then it hits a second layer.
and it gets smaller still. You can probably see where this is headed. Now just imagine doing this not 2 times, but hundreds of times. And this really gets to the mathematical heart of it. As the source material puts it, when you keep multiplying numbers that are less than 1, the result just plummets towards 0, and it gets there fast. So across a really deep network, that strong signal you started with can become, for all practical purposes, nothing. Just gone. So a number gets really small. Big deal, right? Who cares? Well, the real-world consequence of this little math quirk was, and I'm not exaggerating, catastrophic for the ambitions of AI researchers. It was a total showstopper. The most immediate result is that the first layers of the network, the ones that are supposed to learn the absolute most basic fundamental features like edges and colors in an image or basic sounds in speech, they get completely frozen in place. They just don't get a meaningful signal, so they never get any smarter. The entire network is essentially handicapped from the get-go. Now, don't worry about the crazy math on this diagram. The main takeaway here is just to see how this visually represents the network getting stuck. Because that learning signal has vanished, the whole system can just fall into one of these ruts and can't get out. It's like a car spinning its wheels in a ditch. It's burning fuel, but it's going absolutely nowhere. It can't learn. And for any task that relied on memory, like understanding a simple sentence, this was devastating. It meant a network could literally forget the beginning of a sentence by the time it reached the end. It couldn't learn what we call long-term dependencies, which basically put a hard ceiling on how smart these models could ever hope to be. They essentially had a form of amnesia.
But, and this is where the story gets really, really good, things changed. Researchers didn't just give up.
Instead, a whole wave of brilliant, clever innovations came along that piece by piece solved this problem and finally unlocked the true potential of deep learning. And what's so cool is that it wasn't one single magic bullet that fixed everything. It was a whole toolkit of different ideas. The solutions came from every angle you can imagine: completely new ways of designing the networks, smarter individual components inside the networks, and even just better techniques for training the whole thing. One of the early heroes was the LSTM network. This was this ingenious new architecture designed specifically for those sequence tasks. It included these special memory cells that could basically hold on to important information for a long time, creating a kind of separate protected path for the signal to flow down, keeping it safe from vanishing. Then you have another total game changer: residual connections, or ResNets for short. And this was such a simple but powerful idea. They basically created express lanes, or little shortcuts, for the gradient. This let the learning signal literally skip over some layers, bypassing all that repeated multiplication and arriving at the early layers almost perfectly intact. Even really small changes had a huge impact. Just switching out one component, the activation function, which is the part that decides if a neuron should fire or not, made a massive difference. Newer functions like ReLU, which stands for Rectified Linear Unit, just don't squish the signal nearly as much as the older ones did, which helped keep that gradient strong as it traveled backward. So when you put it all together, these new architectures, the smarter components, the clever training methods, and of course you throw in much, much faster computers, the beast was finally slain. They managed to tame the gradient, and that's what allowed us to finally build and train the incredibly deep and powerful networks that are literally changing the world today. Which brings us to a final thought, doesn't it? The vanishing gradient problem went from being this impossible, field-defining barrier to a solved chapter in AI textbooks. It just makes you wonder, what are the seemingly impossible problems that we're staring at right now that will become the solved chapters of tomorrow? What's the next great challenge holding AI back?